This program is brought to you by Stanford University.
All right. Somebody asked me some questions which I thought were good questions, so I asked them to write them down and list them. One, and I thought I would answer them in class because other people might be interested. One, does the apparent wavelength of the cosmic radiation depend on the motion of the observer? I.e., is there a Doppler effect? If so, doesn't that mean there is a preferred frame, the one in which the wavelength is the same in all directions, neglecting the small fluctuations? All right, so the question is, it's a good question, it's a right question, and the answer is yes to almost all parts of it, except where the author of the question realized that the answer must be no. All right, so there's a lot of matter around, and also photons all over the place. And the photons are isotropic. What does that mean? The typical energy of a photon coming from the left is more or less the same as, not more or less, is about the same as the typical energy of a photon coming from the right. The temperature of the photons is pretty well described by the average energy of the photons. And so if we're way, way out in outer space, intergalactic space, I'm not talking about the photons that come from the sun or from stars. I'm talking about the cosmic microwave background, that which is there when everything else is removed, so to speak. Those photons appear to be isotropic. They come at you from every direction with about the same energy, but then that means something a little puzzling, not too puzzling, but a little bit puzzling. If you are moving through this mess of stuff, including photons, mainly photons, and you are moving through it, let's say, to the right with a large velocity, large means comparable to the speed of light, or some fraction of the speed of light, then because of the Doppler effect, you would see the photons coming from this direction as having shorter wavelength, meaning somewhat bluer, than the photons coming from the other direction. Yes, somewhat bluer, meaning to say that you would have a bias in directions in the sky where in some directions you would see hotter photons, higher energy photons. In other directions you would see lower energy photons. Yes, this is true. That is really the way it works. We are moving through the microwave background, our planet, moving with the solar system rotation, with the galactic rotation, and with the motion of the galaxy and the clusters of galaxies. And in fact, when we look at the microwave temperature in different directions, it is not the same in all directions. One direction is preferred. I couldn't tell you which it is offhand. I mean, you know, I don't remember. But it is got to do with known motions of the Earth. And so the answer is yes, there is such a Doppler effect, and yes, there is a preferred frame of reference. The preferred frame of reference is the one where the microwave background looks isotropic from all directions. It happens to be, and this is the key point, it is the same preferred frame of reference as defined by the galaxies themselves on the average. The galaxies are at rest at any particular place. The local galaxies are on the average at rest in some frame of reference. That's a preferred frame of reference, and it's the same preferred frame of reference that the cosmic microwave background is isotropic. So that's the answer to question number one. Yes, there is a special frame of reference. If not, that's even harder to understand. Yeah, fortunately, we don't have to get into that part of the question. Next question. Is there anything in relativity to limit the relative velocity, or can two coordinate points, let's just call them galaxies, can two galaxies have a relative velocity greater than c, greater than the speed of light? The answer is yes. If they're far enough apart, This is just the Hubble law, and the Hubble law holds on distances which may be arbitrarily large, we don't know for sure, but there's nothing wrong with extending the Hubble law out to distances such that velocity is equal to Hubble times distance. If space is as flat as it appears to be, and it does appear to be flat, then there's no obvious bound, certainly nothing within observation, no obvious bound on distances. If distance is big enough, then the velocity, the relative velocity of us relative to some distant galaxy will exceed the speed of light. Can't do anything about it, it's true. Einstein never said that that was impossible. Let's put it this way, what he would say was impossible is for one thing to pass another right in front of your nose at faster than the speed of light. It doesn't say anything about very distant things moving relative to each other with greater than the speed of light. But of course, if something is moving faster than the speed of light away from you, and assuming that it continues to do that, then it can never send a message to you, because if it's moving away from you with faster than the speed of light, then light rays which are sent to the left and light rays which are sent to the right will be both swept along with the motion and effectively be moving away from you. So there is no such cosmic limitation on whether distant things can be moving away from you. The place where they're moving with the speed of light relative to you is a horizon. Yeah.
Wouldn't the light ray sent in the reverse direction,
Back toward you?
right?
Yeah.
Wouldn't that still be traveling at c towards you, but stretched in wavelength to where it is no longer light?
It's actually moving away from you. Well, let's put it this way. Let's put it this way. Okay, the light ray is moving that way, but space is growing faster than the light ray can overcome. Okay? So there's a model for this which I like. It's a model which I invented in order to explain inflation, but let me explain what the model is. Imagine you have a line, and now you start stretching the line. The line is made up out of atoms. Okay, the line is made up out of atoms. And now you start stretching it. What happens? Eventually it'll break because the distance between the atoms will grow larger than the atomic forces can handle. But we also have, secretly, a source of extra atoms. And every time two atoms gets further apart than a certain distance, we put another one in. Everywhere that it happens, we keep filling it up with more and more atoms so that the line continues to grow, constantly being resupplied with atoms. Okay, now it's not atoms really that we want to think about, but it's a good model for it. Then this line will grow, first of all, according to Hubble's law. It will also grow exponentially. The distance between any 2 points will grow exponentially. And there will be some distance beyond which two things will be receding with greater than the speed of light. But if you go to those places, you can ask, supposing here's where the velocity of separation gets to be about the speed of light. If you go to the left and you send a light beam, you can still certainly send a light beam this way, and you can send a light beam that way. The only problem is the atoms are filling in so fast that the distance between you and where the light ray has gotten to is growing faster than the light ray can overcome.
Can I ask you a question?
Yeah.
Does the relativistic formula for the addition of velocities hold?
Locally, at a point, yes.
But
In other words, if we have three observers, And they all pass each other, one after another after
Well, it
another.
only holds in that, but it doesn't hold in the case of velocities exceeding the speed.
Yeah, that's right. You have to go back to first principles again. Yeah, and there you have to use some more fancy geometric. Yeah.
If you have two photons that are radiated from a point,
Yeah.
their separation velocity is 2c.
Yes.
So,
As seen by you.
as seen, right.
Yeah.
And you can't.
Yeah, but you could send something out with 3/4 of the speed of light that way, and 3/4 of the speed of light the other way, and their relative separation to you will seem to be 1.5 times the speed of light, but to one of them looking at the other, it looks less than the speed of
Well, you
light.
can't
So
really.
this is different.
And a photon itself doesn't have an inertial reference frame.
Well, it's moving with the speed of light. Right. So the point is you can't answer questions like this just using ordinary special relativity. You have to use general relativity. And general relativity allows the metric of space to expand. When the metric of space is expanding, that's very much like this picture where molecules are filling in the gaps in between. For example, if this were an ordinary line of atoms, there would be a maximum velocity on it. What would that maximum, an ordinary maximum velocity? The speed of sound on the, or the speed of waves which vibrate on the string here. We could take it to be the speed of sound. Ordinary signals sent back and forth by elastic vibrations or sound waves and so forth also have a limiting velocity. As long as you're not stretching the string and filling it in, then no signal, other than a supersonic signal, no signal which is restricted to be moving slower than the speed of sound for some reason, I was going to say, no signal which is moving slower than the speed of sound can exceed the speed of sound. That's a true statement. But now, imagine this thing is being filled in the way that I described. What is the rule? The rule is that the sound waves relative to the local molecules can't exceed the speed of sound. That's going to be our rule, right? The sound waves themselves, propagating from one molecule to the next, move through this material with the speed of sound. And let's also suppose that nothing else can move faster. Nevertheless, if the string is big enough and long enough, distant parts of it will be moving away fast enough that they'll be moving away faster from you, just because more and more is filling in. It's filling in so fast, and so much of it is filling in, that a point sufficiently far away will be moving away in a way that sound cannot get back to this point. It tries to get back to that point. It moves in this direction, but by the time it's moved 1 meter in this direction, more than a meter's worth of new molecules have been inserted. All right, so general relativity, which allows space to behave in this way, does allow objects to exceed the speed of sound, or speed of light, excuse me, in this sense, but not relative to the local observers. So no observer over here can see a sound wave going past him with faster than the speed of sound.
Are you saying that recession is a kind of drag?
Is it a kind of drag? It is what it is. No.
The stretching of the wavelengths due to the expansion, is that due solely to expansion, or is there another element to it?
It's solely due to the expansion, but it's not distinct from the Doppler effect. It's the same effect. You can solely think of it, if you want a simple way to think about it, just think about it as being due to the expansion. So a wave on here, when the system expands, the wave expands with it. That's the simplest way to think about it. It's, yeah.
Is that statement you just made, is that theoretical, is that just an empirical statement, or is that
Which is an empirical statement?
that the waves the wave stretches as the universe stretches.
No, it's a theoretical statement based on the general theory of relativity combined with the theory of waves propagating in an expanding space. No, it is part of the mathematics of the general theory of relativity, of expanding space-time. If you write a wave equation in a geometry which is expanding, you will find the waves expand. So it's not is it an empirical fact? Well, yes, but not in the sense that we can actually expand space and see the wavelength expanding. It's an empirical fact, an astronomical fact, but it's also a deeply theoretical fact that would be very, very surprising if it were false.
This idea is predicated on the idea that atoms fill in the blanks as a stretch. Is that what's really happening out in the cosmos?
No, it's not atoms. Little bits of space, little bits of newly formed space. That's one way to think about it. The other way to think about it is just through the equations of general relativity, in which there is an expanding metric. This is the expansion factor, the scale factor. And the expansion of the scale factor just produces more and more space. If you like a model for it, people like models. Is it like expanding a rubber band? No, because rubber bands have this habit of thinning out when you stretch them. And let's forget whether they break. Somebody living in that rubber band would notice the fact that with time, the interaction between neighboring atoms changes. He would notice with time the properties of the space that he lives in changing. Okay, that's not the way general relativity works. It works more like the situation where there's a hidden reservoir of points that you can keep inserting so that as time goes on, the properties that one ascribes to a region of space don't change. Space doesn't thin out in that sense. That's the way the mathematics works. This actually would be very, very useful. Exactly these equations would be rather useful in describing a line of atoms. If you really did insert more and more atoms, they would be described by those equations. Anyway, next, let's see, did we finish the questions? Yeah, okay. Alice and Bob, from the first lecture, is there a relationship between the relative velocity exceeding c and the surface of last scattering and the size of the observable universe? In other words, coming back to this question of, here I suppose is Bob, Alice is moving outward. Well, according to the Hubble law, there is some distance out there. Here's Bob. There's some distance out there where things are just moving away from him faster than the speed of light, and he can't get signals from them. Alice, let me get the question again. Is there a relationship between the relative velocity exceeding c and the surface of last scattering? Yeah. So there's some distance. When Alice is beyond that distance, her light waves cannot get back to Bob. Okay? That's called the horizon. Okay, that's called the horizon. We're going to have more to do with the horizon, but that's just called the cosmic horizon. And if space is expanding in the right way, then that cosmic horizon has a fixed size, and it just sits there, and Bob is surrounded by it, and anything out beyond that horizon is just invisible to him because the light can't get back. Now, that distance is the place where the Hubble law says, that distance d is the place where the Hubble law says that the velocity of recession becomes equal to the speed of light. It is not quite the place where the surface of last scattering is. The surface of last scattering is slightly in. Slightly in. It is the place where if a light ray was emitted from that place, by the time it got to us, its wavelength would have been infinitely stretched. That's what the horizon is. Any light ray emitted from the horizon, by the time it would get to us, why would it be infinitely stretched? Well, the reason is fairly simple. A light ray emitted from very close to that point takes a very, very long time to get to us. If it takes a long time, then the amount of stretching that it undergoes is enormous. But the other way to think about it is Doppler shift. Anything that's moving away from us with close to the speed of light will emit Doppler shifted radiation that we'll see stretched. So things coming from the horizon, that's the place where things are infinitely stretched. That is what the horizon is. The horizon is not quite the surface of last scattering. How do we know that? Well, the light from the surface of last scattering, we see it. It is not infinitely, we don't see it with our eyeballs, we see it with infrared detectors. It's not infinitely redshifted. In fact, it's redshifted by about a factor of 1,000. It's 1,000 times longer wavelength by the time that it gets to us, we discussed this, than it was when it was emitted. 1,000 is a big number. To the extent that 1,000 is a big number, the surface of last scattering is very close to the horizon, where the redshift factor would be infinite. So for many practical purposes, the surface of last scattering is at the horizon, or close enough to it. Yes, that does define the size of the observable universe. That's exactly what the observable universe is. It's a portion of the universe that light can reach us from. So it's the portion of the universe within our cosmic horizon. Yeah.
Question, in a box, let's say, there's a longest wavelength that can happen, you know, I think half the distance or whatever. Could you extend that to the universe?
No, you see, not really. Here, imagine this again. There's nothing to forbid you from having an arbitrarily long wave embedded in this thing here that's even larger than the horizon. It's not like being in a box. Not quite like being in a box. So a little bit different. Okay, let's see. Is there any last question?
There are things that eventually become invisible. We can see the day that will be invisible.
Yes, that's right. Distant galaxies will someday pass beyond the horizon. And will, not only distant galaxies, even relatively close galaxies will pass behind the horizon.
That was my question. The D in that, since H is going to be a function of time, is D getting shorter?
Oh, okay. Well, we'll come to that. I said H in principle can be a function of time, and it is a function of time. What we know about the universe today, if it continues the way it's going, is H is asymptotically going to a constant. So at late times, you can think of H as a constant. That's the accelerated expansion, which we're going to come to today. H is tending toward a constant. That's right. So once H becomes a constant, then this becomes a relationship between distance and speed of light.
Does that mean that we won't be able to see the microwave radiation eventually?
The microwave radiation will get stretched and stretched and stretched and stretched exponentially, and so it'll just fade out of existence.
So that's going to fade out of existence before nearby galaxies.
Yeah. Well, a nearby galaxy will disappear. Will it fade out of? Depends on how good your detectors are, obviously. Yeah, I would guess it will become undetectable before the galaxies. Right.
Because the microwave...
I'm not sure which goes first, the galaxy.
Well, it would seem like the microwave radiation is coming from even more remote things than nearby galaxies. So if we're not going to be able to see them,
Oh, by the time the galaxies, but yeah, I think that's right. Yeah, right. So everything will cool down, everything will disappear behind the horizon. Only the things which are accidentally more or less gravitationally bound to us, the solar system won't fly apart, the galaxy won't fly apart, but the distant galaxies will all recede and will eventually be left as a truly isolated island with nothing to tell us that those other galaxies are out there, except history books. All right, look, I wanted to get on to some more things about cosmology. Now, we're going to get just a little bit technical today, not too technical, but there are pieces which are essential. The name of this series of courses, at least in my own mind, are the theoretical minimum, the minimum number of things you need to know in order to really understand the next step. And the next step would mean following a serious cosmology argument. So I don't skimp on the essentials. When the essentials are hard, I do them in the simplest, cleanest, least technical, least mathematical way that I can, but I try to do them preserving the essentials. We're going to do that today. The other thing I don't like very much is lots of jargon. But sometimes it's useful to tell you about the jargon so that when you read about astrophysicists determining that W is equal to -1, you may want to know what W is. And in order to tell you what W is, I will have to tell you what the definition of W is. But there are 6 things which are all pretty much the same with different letters that describe them. So I've sort of, somebody will put this on the web, and it's got some definitions and so forth. All right, but enough excuses. Let's get down to it. What I want to talk about is the relationship between pressure and energy. No, let's go back a step. We're late. We're late. I'm going to start the class now. We're going to stay a little bit late today because I want to deal with some issues here. Let me just do a very brief review. So far, we have found 2 kinds of matter which can cause the universe to expand. One of them was radiation, and the other was just ordinary atoms sitting still, moving together with the galaxies. In fact, they are just the galaxies. One, I think I named matter, a matter-dominated universe, a universe which is dominated, whose energy is dominated by things which are more or less standing still in their own reference frame, even though the entire universe is expanding. As we move along with the expansion, things standing still, massive objects, their energy is simply their mass, and a universe based on that kind of energy density is called matter-dominated. Right? There's an energy density. Let me just write the fundamental equation over here. The fundamental equation that we've been working with is that the scale factor squared, the ratio of the square, this is the Hubble constant squared, that's equal. Incidentally, can green be seen well? Does that work? It's okay. It's not as good as black? Let me try black. The trouble is the black ones have always run out of ink. A dot over A squared, that's the Hubble constant squared, is equal to 8 pi g over 3 times the energy density. As always, the speed of light I'll set equal to 1. 8 pi g over 3 times the energy density. And that's our basic equation for how the universe expands. A is simply the scale factor, expands or contracts or whatever it does. All right, the energy on the right-hand side can come from various components, And in standard cosmology, what's called the standard model of cosmology, there are basically three components to the energy density on the right-hand side. The first is matter. Now, matter is by definition particles or objects. It could be black holes, it could be galaxies, but objects that are at rest moving, and at rest means moving with the overall expansion. That's called matter, such things. And the universe that is matter-dominated, let's write down what it means. It first of all means that the energy density goes like some constant divided by the cube of the scale factor. The cube of the scale factor is just the volume, and if the number of particles within the volume stays fixed and the mass of each particle stays fixed, then the energy density is just the mass within that region. I guess I called it m at one point, the mass within the region, divided by the volume of a co-moving piece of space. And that's just A cubed. So this is matter-dominated. And we solved the equation with that particular setup. And what did we find? We find that the scale factor grew like t to the 2/3. Next, we introduced another kind of energy density, radiation, made up out of photons. Because the energy of a photon decreases when a volume grows, imagine a box, imagine expanding the box, each photon's wavelength grows, its energy decreases, and so as A increases, this is, let's call this matter, rho, let's call it radiation, energy density in radiation, instead of being 1 over A cubed, is some constant divided by A to the 4th power. It's the 4th power because each photon has an energy which decreases as A gets bigger as 1 power of A. This is the radiation dominant. If all there is radiation and no other kind of energy in the universe, then it's called radiation dominated. Of course, you can have both together. Then the equations get more complicated, but in that circumstance, A grows like t to the 1/2. Now, the smaller A is, the bigger the radiation component is relative to the matter component. The smaller A, when A is very small, this is bigger than this. So that means in the very early universe, the universe was radiation dominated. After a time, the individual photons lost their potency because they expanded, and the universe became matter-dominated. And so it made a kind of transition, not a sudden transition, a smooth transition, from an expansion like square root of t to an expansion that was t to the 2/3. This is a little bit faster expansion than this. And that happened after about 10,000 years, pretty early. At least according to the parameters as we now know them. We actually can't see back to that point, but we can infer it by a variety of arguments. All right, there is a third component of energy that's important in the universe. Of course, there's zillions of components. Right? But the important, dynamically important components that really govern the way the universe behaves on a large scale is what I'll call rho naught, and that's vacuum energy, dark energy, cosmological constant, all the same thing, and we're going to come to that tonight. What I will tell you about it is it doesn't depend on A at all. It's energy that's there in the vacuum. Think again about this growing chain of atoms. Waves along here, sound waves, would get less and less energy as they got longer and longer wavelength. So they, in fact, the energy density would decrease with time from a sound wave. Let's suppose that there were embedded in this string a set of impurities. These impurities, we do not have a source of new impurities. We don't have in our pocket a source of these new impurities. Let's give those impurities names. Let's call them hydrogen. Okay? They're hydrogen, or we could call them galaxies, or just ordinary stuff. Right? What happens as more and more points fill in here, points of space fill in, the atoms get further and further apart, and so again the energy density decreases. But there is also just the energy density. I shouldn't have called them atoms. I wanted to reserve atoms for the little rubber molecules that were in here, that we're adding into it. These are galaxies. Galaxies, galaxies. The galaxies get thinned out by expansion, and so their energy decreases. That's why it decreases here. The sound waves, the number of waves that can fit in, the wavelengths get longer and longer. The sound waves get less and less potent, less and less energetic. So radiation, which is the analog of the sound waves, also the energy density decreases as A gets bigger and bigger. But we can just imagine that there's some kind of energy associated with the material that the string is made up out of. It doesn't change with time. It doesn't dilute. It doesn't dilute because every time it tries to dilute, we put another atom in there. The atoms themselves, the rubber atoms, let's call them rubber atoms. Make believe the string is made of rubber. Every time the distance between rubber molecules increases, we throw another rubber molecule in there. So what happens to this component of the energy, the component that is associated with the rubber molecules that we put in? That does not go away as the universe gets bigger and bigger. It stays constant. What's going on locally within that rubber string never changes with time. And so this so-called vacuum energy or dark energy, it's the component which does not go to zero as A gets bigger. It's just a constant. In fact, you can think of it as a constant of nature. It's a number. It's there. It's there in the vacuum. It's peculiar. You may find it odd. I'm just going to write rho naught equals rho naught. It doesn't change. Those are the three components of energy which are important in the evolution of the universe. We're going to talk about them individually now. Now, with each component of energy, these are the energy densities, of course. These are the energies per unit volume. With each component of energy, there is also a pressure that's associated with it. Let me begin. I want to describe how energy is connected with pressure. Pressure is important in cosmology. So let's talk about the relationship between pressure and energy density. Particularly, let's start with radiation. Let's start with radiation. I'm going to start with a one-dimensional box. A one-dimensional box is just a line segment. Let's imagine that it's actually a finite line segment. For the time being, it's not growing, but it contains photons going back and forth, and the photons move with the speed of light. Every photon has an energy, and when the photons bounce off, let's assume that they bounce off the walls of the box. The walls of the box are just the ends of the interval. What happens when a photon bounces off the end of the, when it bounces off the interval? It creates a pressure. It creates a pressure. It creates radiation pressure. Light bouncing back and forth between mirrors exerts a pressure on the mirrors. It's that radiation pressure which I want to, and the relationship between the radiation pressure and the energy density in there that's going to occupy us for a while. So let's see if we can figure it out. The formula, what we're interested in now is the force on the wall of the box, the average, the time averaged force on the wall of the box due to the photon bouncing back and forth. For the moment, just one photon. Later on, we'll fill it up with lots of photons. All right. What is the equation for force? Force is equal to the time rate of change of something. What is it the time rate of change of? Momentum. P. Why does the momentum of a photon change? The momentum of a photon changes because the photon is originally going to the right and it changes to the left. Supposing, let's call it small p. Small p stands for momentum. Large p will stand for pressure later. Pressure and force in one dimension are the same thing. All right, so let's think of the photon rattling back and forth many times. Each time it hits the wall, what's the change in the momentum of the photon? If the photon happens to have a momentum p. 2p. Okay, so if the magnitude of the momentum is p, when it reflects, there's a change in momentum twice p. What's the time interval between successive jolts at the end of the box here? The photon moves with the speed of light, and the distance is L. So how long does it take between collisions with the wall? 2L over C. Why 2? Why 2? Because it's got to go and come back. All right? So the rate at which momentum is being, if you like, which momentum is being deposited on the wall, or the time, the momentum per unit time that's changing by virtue of the reflection, is twice p, but it happens every, what did we say, L over C? 2L over C. All right, the 2's cancel. And we can write this in the form PC divided by L. That's the force on the wall of the box. Now, next question. What is the relationship between the momentum of a photon and the energy of the photon? Anybody know? We've done this a number of times. In fact, I think I'm not going to work it out. Let's just state what it is. The energy of a photon is its momentum times the speed of light. Let's just check its units. It's easy to check its units. Ordinary momentum is mass times velocity, right? All right. Supposing we multiply that by another velocity. Here's momentum, and we're multiplying it by another velocity. Then it will have units of mv squared. But mv squared obviously has units of energy. It's the kinetic energy. So momentum times speed of light does have units of energy, and it is the energy of a photon. Its momentum times its velocity is its energy. So we can rewrite that the force on the end here, this is the force, that's PC over L, that is the energy of the photon divided by the length of the box. Well, the photon rattles around many, many times, and we average over long periods of time. What is the energy divided by the length of the box? It's the average energy density. The energy divided by the length, the average energy per unit length. So we found out that the force in this simple example with just one photon rattling around, the force is just equal to the energy density, and that's it. Force, and let's call it rho. Rho for energy density, but let's keep in mind that in this example, energy density means energy per unit length, not per unit volume for the moment. Energy density, rho stands for energy density. Now supposing there's a lot of photons in the box. Each photon exerts a force when it bounces into the end, and each photon has an energy. For each photon, the force that it exerts is equal to the energy divided by the length. So when I add them all up, it will still be true that the total force will equal the total energy divided by the length. So this formula is not necessarily the formula for a single photon. In fact, for a single photon, it's kind of a little bit funny because everything happens in jolts that take a long time between jolts. But if you have a lot of photons in there and they're all doing the same thing, then it gets smoothed out, and the force or the pressure at the end is simply equal to the energy density. Okay? That's the one-dimensional case. Now let's think about any questions about this. All right, this is a fundamental fact, and it's true in any number of dimensions, not specifically this exact fact, but similar facts are true in any number of dimensions, that energy density and pressure are closely related. So now let's come to 3 dimensions. Let's take, instead of a line interval, let's imagine a box, a 3-dimensional box. And for the moment, let me suppose that all the molecules, not the molecules, the box is full of photons, uniformly distributed, but let's make a simple wrong assumption. The simple wrong assumption is that all the photons are moving only along the x-axis for the moment. Suppose they only move along the x-axis. The box is full of photons, but let's take all those photons in a narrow, what do you call such a shape? A rectangular parallelepiped, I believe. All right. Let's take all the photons in there, and let's assume, as I said, wrongly, that they're all moving only in the horizontal direction. Then we can say exactly the same things, except we really should say it in the following way. Let's take a little element of area here. Here's a little element of area, and take all of the photons in that little element of area. I'm not going to write that as rho times the length, because I'm now going to think of rho as, I'm going to think of rho as the density per 3-dimensional volume. All right? What is the corresponding formula? Well, we can write it the same way. The force is equal, it is in fact equal, to the energy in that rectangular hyperbola divided by the length. That hasn't changed. But now I want to divide both sides of this. Oh, sorry, that's divided by the length. Now I want to divide both sides of this by the little element of area. So let's divide it by the little element of area there. A stands for a small area now. And now, what's the length times the area? That's the volume in this region here. What's the force divided by the area? That's the pressure. That's the definition of pressure, force per unit area. So we come to pressure, not momentum now. I think I used small p for momentum, yeah. Pressure is equal, again, to energy divided by volume, which is again rho, but now this doesn't mean energy per unit length, it means energy per unit volume. Now what's wrong with this? This is a funny setup here. I have pressure on the ends of the box here, but if there are no particles going vertically, bouncing off the roof and the floor, there will be no pressure on the roof and the floor. We know from experience that, that a nice thermalized distribution of molecules or photons or whatever they are will exert equal pressures in all directions. So let's imagine now, here's an oversimplification, but it's closer to the truth. Let's suppose that there are photons which move along the x-axis, photons which move along the y-axis, and photons which move along the z-axis. This, of course, is still an oversimplification. The typical photon will be moving in some oblique direction, which is neither x, y, or z. But let's just take this simple case here, where there are equal density of photons moving vertically, horizontally, and in and out. Same density of photons. And what will the right equation be? Well, only those photons which are moving horizontally will contribute to the pressure on this wall. Only those moving vertically will contribute to the pressure on the ceiling. Only those moving in and out will contribute to the pressure on the front wall. So what's the right formula? The right formula is the pressure is equal to the energy density divided by 3. 1/3 of the photons are moving this way. They all have energy. All of them have energy. But only 1/3 of them contribute to each component of the pressure. So the formula would be, in this oversimplified setup, rho divided by 3. Now, is this, the setup was oversimplified. The answer is correct. The answer is correct. The answer is correct no matter what directions the photons are moving in, as long as they're all scrambled up enough. The right answer, of course, is a given photon is moving in some random direction, but it has an x component of momentum, a y component of momentum, and a z component of momentum. The total energy is whatever the total energy is, but it works exactly as if 1/3 the photons are moving this way, 1/3 the photons are moving this way, and 1/3 the photons are moving the other way. So this is a correct relationship. I don't want to do it in detail. It is a correct relationship. Really, it's just that on the average, 1/3 of the energy is going into motion in this direction, 1/3 is going into this direction, and so forth. All right, so P equals rho over 3. Let's write that down over here. Pressure for the radiation-dominated world is energy density, radiation, divided by 3. What about the matter-dominated world? The matter-dominated world is a world in which atoms are there, or galaxies, objects are there, but relative to the box, if you want to imagine what the box is a certain region of space that's moving along with the flow. The atoms are not moving, or whatever is making up the material is not moving relative to the walls of the box. They're frozen, they're stuck. Do they have energy density? Sure. Each one has a mass. Multiply the mass by mc squared. No, don't multiply the mass by mc squared. Multiply the mass by c squared, and you will find the energy of each one. But what about the pressure? Is it exerting any pressure on the walls of the box? No, because they're not banging into the walls of the box. They're standing still. They don't exert any force on the walls of the box. So this limit of very slowly moving particles moving with the flow corresponds to pressure equals 0. Are there other possibilities? Sure. We could heat up this material so that the molecules were moving more, or so that the galaxies were moving more. Then we would have some pressure. And we could get sort of halfway in between. We could have a parameter, the temperature of what's going on in here. When the molecules are cold, hydrogen is cold, or the galaxies are cold. What does cold mean? Cold doesn't mean that the stars are cold. It means that they're not moving relative to the ambient background. Cold molecules don't exert pressure. Fast molecules exert pressure. Speed of light sort of is a limiting case. The pressure is fairly large, yeah.
In the case of expanding universe, right, aren't
Yeah.
particles actually moving apart?
Yes, they are, but you take a small enough box, take a small box so that we don't have to worry about the growth of it, and examine this for an infinitesimal box. For an infinitesimal box, this will work. Okay, so here we have P equals rho over 3, radiation over 3. Here we have P equals 0. And I'm going to write a more general equation. I'm going to write the equation that the pressure, this not associated with this third line yet. Let's erase the third line. We don't know about the third line yet. Not erase it, just put it down here. Rho naught. Let me write a general equation. It's an equation which covers a lot of different assumptions. It is the pressure is proportional to the energy density, rho, whatever the energy density is, times a numerical factor, W. What is W for the cold gas? 0. W equals 0. What is W over here? A third. W is a parameter which, when you vary it from one thing to another, you can cover a lot of ground about what the material which is driving the universe is. For example, something between 0 and 1/3 would describe something called warm dark matter. If dark matter is not thought to be warm, dark matter is thought to be just as cold and correspond to P equals 0. But for a while, people thought that dark matter might correspond to neutrinos. Neutrinos move pretty fast. They whiz back and forth, and they don't quite move with the speed of light. And if that was what the dark matter was, then we wouldn't have P equals 0, because the neutrinos would be moving. We wouldn't quite have W equals a third, because that corresponds to motion with the speed of light. We would have something a little bit less than a third. So there's a wide variety of different kinds. This is called the equation of state. W is the parameter in the equation of state. That's just terminology. And W is just terminology. But if you want to follow what's going on in cosmology, and the article says, well, there's something or other called W, and astronomers are measuring it to equal something or other, you want to know what it is. So that's what W is. Okay, so that covers the different kinds of equations of state. But now let's come to, I want to continue with this line of reasoning about the equation of state. How is W related? Notice that there's a relationship, or could be a relationship, between what W is. When W is equal to 0, it looks like the energy density goes like 1 over a cubed. When W is equal to 1/3, it looks like it goes 1 over a to the 4th. Is there a pattern there? Is there some reason that as you vary this W, the energy pressure ratio, is there some reason that governs how the energy density changes with A? And the answer is yes, there is a relationship. I'm going to show it to you. It's tricky. It's not hard. No fancy mathematics, no fancy calculus, just subtle. It's a little bit subtle. A little bit of calculus, but nothing fancy, but some subtle reasoning. It's called thermodynamics, and thermodynamics is always hard. Not because it's mathematically hard. This is very easy thermodynamics, but nevertheless, a little bit hard. Let's take a box. This box does not have to be a cube. It could be any shape, whatever. All right, and expand the box a little bit. We could expand the box by moving one wall out a little bit. We could move all 3 walls out a little bit. But what we're doing is just increasing the volume of the box. there's molecules on the inside. Molecules or photons or whatever. There may or may not be, and typically there will be, pressure on the walls of the box. Pressure on the walls of the box. When we move the walls of the box, we do some work on the walls. The pressure on the inside pushes against the wall and does some work. How much work does it do? Let's see if we can figure out how much work it does. Supposing this wall moves by a little distance called dx. Only the x wall moves a little bit. We move the x wall a little bit. How much work is done on the x wall by moving it a little distance dx? Force times dx. That's the work done. What's the force? Pressure times area. So the work done on the walls of the box is the pressure times dx times the area of the wall. What is dx times A? That's the change in the volume of the box. So it's pressure times the change in the volume of the box. You would get the same thing if you moved the vertical dimension a little bit or the in-out direction a little bit. In fact, you would get the same thing if you changed all the directions simultaneously. The work done is the pressure times the change in the volume. Now, where does that work come from? Energy conservation tells you what is that work? That work is the increase in the energy of the walls of the box. Where did it come from? It got robbed, or the internal energy in the gas, whether it be photons or whatever it is, got robbed of a little bit of energy, and that energy went into work. The energy in the box decreased. That is why the temperature of a box goes down when you increase the size of the box. The internal energy decreases. So we can write the decrease in the energy of the box is PdV. Why the minus sign? Because the energy of the box goes down a little bit. All right. This is a very general fact about gases of all kinds, that the change in the internal energy, when you just shift the walls a little bit, is just PdV. This could be a spherical box. Let's take it. It could be a spherical box. It could be a cubical box. It doesn't matter. And we might also write that, well, later on, let's do it now. No, let's leave it this way for a moment. Later on, we're going to write that the volume of the box is A cubed, A being the scale factor. Later on, we'll think of this as a box, one scale factor on a side. But for the time being, it's just that. Now, what is the energy in the box? The energy in the box is the energy density times the volume, right? E is energy density times volume. So what is the change in energy? If energy is rho times V, and we don't know offhand, rho may change a little bit. We know that the energy is going to change. It may change because rho changes, or it may change because the volume of the box, or maybe both. So we should write that the change in the energy of the box is equal to rho dV plus V d rho. That's just the change in a product when you change each term, each factor a little bit. Just elementary calculus. dE equals rho dV plus V d rho. Okay. And that's equal to minus P dV. Let's take everything with a dV, with a d volume, and put it on the right-hand side. Then we get volume times dP is equal to minus P plus rho times dV. VD rho, sorry, VD rho. I have written in my notes here, which you will get a copy of over the internet or something, I have P equals 1/3 rho someplace, and then I've put in brackets P, P-E-E, equals 1/3 rho, RH rho, so that I wouldn't make that mistake. Right. Rho and P are not the same thing. V d rho equals that. Right. There's an equation. Now, let's remember now that for a lot of interesting situations, where is it? That P is related to the energy density by a numerical number W, which happens to be 1/3 for photons, happens to be 0 for cold, motionless matter, and it could be other things. So let's plug that in. Let's plug that in. And we get an equation. V d rho is equal to minus. Now, let's see. P is W times rho. So I think I will write that this is W plus 1 rho dV. Does everybody see what I've done? I've simply said that W times rho is equal to P. If I happen to know what W is, then this equation can be nicely solved. I'll show you the solution. The solution we write, I'm going to do a little bit of differential equations here. We can write d rho over rho is equal to minus W plus 1. W now is a number. W is a number. dV divided by V. I've divided by V and I've divided by rho. All right, for those who know enough calculus, what is d rho over rho? It's the differential change in log of rho. So this is the change in log of rho minus W plus 1. What's dV over V? D of log V. This is not very hard to solve. It says that log of rho is equal, equals minus W plus 1 log of V. What, the right-hand side, if I multiply something by the logarithm of V, that's equal to the logarithm of something else. Logarithm of V to what power? Minus W plus 1. Minus W plus 1. All right? In other words, 1 over V to the W plus 1. No, I don't think so. Oh, yeah, there's an additive constant. Yeah, one can add a constant. Won't change anything. Okay, what's the solution to this? Rho is equal to 1 divided by volume to the W plus 1. Let's just write. Just throw away the log, cancel out the logarithms. Rho is equal to 1 divided by the volume to the W plus 1. Let me just remind you what we used. We basically used energy conservation, that the work done in expanding the box is the energy that is robbed from the internal energy, and then we used the relationship between internal energy and pressure. Pressure to tell us the work, and this is the equation, dE equals P dV. And then we used for energy, rho times volume, and for pressure, W times energy density. And that told us that the density behaves like 1 over the volume. This tells us how the energy density changes as we change the size of the box. All right? Now, what box are we talking about? We're talking about a box, or we could be talking about a box, which is 1 unit on a side in cosmology. 1 coordinate unit on a side. 1 coordinate unit on the side, but a box which is 1 coordinate unit on a side in a small amount of time will expand. When that box expands, we apply exactly this rule here. And what does it tell us? It tells us that rho, what's the volume of the box? Proportional to a cubed. If I take a box which is 1 unit on the side, its volume is a cubed. So what does it tell me? Well, there's a constant here. There's a numerical constant. A numerical constant divided by a to the w plus 1. That tells me how the energy density changes as you expand the box. Well, did I get it right? No, I didn't get it right. There's a 3. It's a cubed. V is a cubed, so it's 3w plus 3. Did I do that right? No, 3w plus 3? Yeah, 3w plus 3. No, it's not 3w plus 3. What is it? I've lost something. There's a 4 in there. Where's my 4? 3 times 1 plus w. That seems right. 3 times 1 plus w? Yeah, that's right. 3 times 1 plus w. Okay, let's try it out. Here's w equals 0. That's matter, cold matter. W equals 0, c divided by a cubed. W is equal to 0. 1 plus w is 1. C divided by a cubed. That's exactly this formula here. So we've done a very, very fancy argument just to tell us that if we have a bunch of unmoving particles which exert no pressure, that the energy density decreases like 1 over a cubed. Duh. Okay, let's try it for radiation. For radiation, W is equal to 1/3. This is 1 plus 1/3 is 4/3, divided by 3 is 4. That's a little less duh. A over 4. Okay. So for radiation, it's A over 4. But now you have the tools to decide exactly how rho behaves given any equation of state. An equation of state means a value of W. So you could have other kinds of material, other kinds of warm gas, cold gas, other kinds of mixtures of gases, whatever, for which W might be some other number. If so, you simply plug into this formula, and this will tell you how rho changes with A. What good does that do you? Well, you couple it up again with the FRW equation of motion. Where is it? We've erased it. I think we don't need this anymore. This was the final conclusion. And it's the reason, this tells you why W is an interesting quantity in cosmology. It tells you how the energy density changes as the universe expands. But remember, we have A dot over A squared is equal to 8/3 pi g times rho. So once we know how rho depends on A, we can put it into here. And now, with a little bit of work, we put some constant divided by A cubed to the 1 plus W. And now, with a little bit of work, you should be able to tell me how A depends on time for a given W. How do we do that? We just try out different power laws. T to the 2/3, T to the 1/2. I'm going to leave that for you. All you have to do is plug in A goes like t to a power, plug it into this equation, and require that the left-hand side and the right-hand side balance, and you'll find that this power, I don't remember the detailed relation, this power depends on W. When W is equal to 0, this power is 2/3. When W is equal to 1/2, the power is 1/2. No, when W is equal to 1/3, radiation, yeah. Okay, so you can work that out yourself, and you can find out how the universe expands for any value of W, with one exception. What's the exception? Well, you may have a little bit of trouble. Yeah, you might have a little bit of trouble with -1. Right, with W equals -1. What is W equals -1? Does it mean anything? And is there an answer to the problem? Yeah, W equals -1, we'll see why, is exactly this vacuum energy here. The vacuum energy which doesn't grow or shrink or do anything. W equals -1 just means, if you look at it, W equals -1, that's a to the 0 power, right? If W equals -1, that says that the energy density doesn't depend on A at all. 1 plus W in that case would be 0, and we would just have C divided by A to the 0, and A to the 0 is just doesn't depend on A. All right? So W equals -1 is exactly this situation where rho is constant, where rho simply doesn't change when you expand the universe. It's the situation where the energy doesn't dilute. It's as if you keep putting in new things as the universe expands to make up for the increased distance between things. Is it an interesting situation? Yes, it is a very interesting situation. It corresponds to Einstein's cosmological constant. It corresponds to what's called dark energy or vacuum energy. So it's worth our while to spend a little bit of time working out what happens when W is equal to 0. No, when W is equal to -1. Incidentally, W equals -1, you might say, wait, that's weird. That means that the pressure is minus the energy density. Well, the energy density is positive. This is not the energy density being negative. The pressure is negative. Is pressure being negative weird? How weird is pressure being negative? Well, if you have two walls, positive pressure means pushing against the walls. If you have two walls connected by a rubber band, you have to pull them apart. They're being pulled together. That's negative pressure. All negative pressure is tension, a resistance against expansion. So negative pressure is a perfectly good thing. You take a rubber band and you stretch it, and it's an example of negative pressure. It's pulling the ends together. Positive pressure is that which pushes against the ends. So negative pressure is in itself not weird. As I said, it corresponds to a kind of tension. It's certainly not mathematically strange, and it's common in physics. Pressure, tension. They're the same thing. One is just the opposite of the other in sign. Okay, so let's work out how the FRW equation behaves if W is equal to -1. In that case, the energy density is just constant. So let's just plug in that the energy density is constant. And we've already named it. We've called it rho 0. Rho 0 is a constant. It doesn't, by constant, I mean it doesn't depend on time. It's a constant of nature, if you like. It's something which you measure and it never changes. Why doesn't it change? Because it doesn't dilute. Whoops. Okay. The combination, just as, again, I hate terminology. There's too much terminology. We can't help it because things get named independently by different people, and eventually we just have too many names for things. The combination 8 pi g rho naught has another name. Anybody know what it is? Lambda. Rho naught is called vacuum energy. Lambda is called cosmological constant. They are the same thing apart from some numerical factors. Whenever there is a cosmological constant, it means there's a vacuum energy. Whenever there's a vacuum energy, it means there's a cosmological constant. Now, why lambda was not named 8 pi g over 3 times rho naught, that's a historical fact. We'll find out why Einstein didn't include the 3 here. There's no interesting physics in it. Yeah, I'll tell you what the interesting physics is. Einstein's equations actually look like this. So when Einstein wrote his equations, it was natural for him to define this thing over here. But when he solved the equations, not he, but when de Sitter solved the equations, he put the 3 over here. So lambda is by definition not the right-hand side of this equation. There's an extra factor of 3. All right. Remember, the right-hand side is just a number. The right-hand side is just a number. Don't think about how it changes or anything. It's 7 or 6 or 5 or whatever it is in some units or other. And we can take its square root. And we can write that a dot over a is equal to the square root of this number, 8 pi g over 3 rho naught, or a dot is a times a number. What's the solution to an equation like a dot is proportional to a? An exponential. The time rate of change of a is proportional to an exponential. Now, of course, the combination a pi g over 3, the square root of it, 8 pi g rho over 3, has yet another name. Okay? Let me tell you what the other name is, but we don't need, I can tell you what the other name is very quickly. Let's put it back in this form here. Do you remember what a dot over a is in general? It's the Hubble constant. But of course, the Hubble constant is not typically a constant. But in this case, it is a constant. In this case, the Hubble, this is the unique special case, W equals -1, where the Hubble constant really is a constant. Right? It doesn't change with time. This is rho naught, I'm sorry. Rho naught. So it's sometimes just called h. But if I call it h, we'll lose track of the fact that h already is something which can change with time and so forth. So I'm just going to call it this. And our equation is the time rate of change of a is proportional to a with a numerical coefficient. What's the solution? A equals a constant times what? No, not rho naught. A? E, exponential. When the rate of change of something is proportional to the thing, that's when you have an exponential growth. The rate of change is proportional to the thing itself. All right? And what's the thing in the exponential? E to the, it's going to be e to the time, but there's a time constant. And the time constant is just the square root here. Square root. A dot over a squared. Came from the square there. Not a cube root. What's that? Rho naught. Oops. This rho naught. Inside the square root. All right. Let me write it over so it's clear. E to the square root of 8 pi g rho naught divided by 3, all of which is a number, times t. So, if there is a vacuum energy, if there is a component of the energy, well, here we're just doing pure vacuum energy. In a few minutes we'll talk about what happens if all three of them are present simultaneously. But if there was only a vacuum energy, the universe would exponentially expand, and it would expand at a rate which is governed by this rho naught. Now, the universe, it doesn't expand, doesn't double in size. This is not the e to this number here, or this number here is not the doubling time. It's called the e-folding time. It's the amount of time that it takes the universe to expand by a factor of e. But it's sort of like the doubling time. The doubling time for the universe is not a second, and it's not a thousandth of a second, and it's not 10 to the minus 43 seconds. The doubling time for the universe is pretty darn slow. What's, roughly speaking, the doubling time of the universe? Something about some of the 5-10 billion years of order the age of the universe, which sounds like an accident, and it doesn't seem like an accident. More or less accidental at the present time that the age of the universe and the doubling time are about the same. That means that rho naught is very, very small. Rho naught, thought of as an ordinary energy density, is very, very small. But of course, what it's competing with is other very small energy densities. The energy density in the universe due to ordinary matter and galaxies and so forth is very, very small. Galaxies are far apart. And so the question comes up, which one of these is present? The answer is all of them. And let's discuss, well, let's first of all add this in. Rho naught equals, I'm just going to write rho naught. This is called vacuum dominant, the vacuum dominated universe. And its A is equal to e to the square root of 8 pi g rho naught 3, I'm not going to write it, times t, exponentially increasing. And this corresponds to W equals minus 1. P equals minus rho. Okay, that's the basic idea of vacuum energy. Yeah.
So doesn't that mean that eventually, even if rho is very small, that the vacuum...
It doesn't mean what?
Doesn't mean that eventually, since it's exponential, it'll overwhelm the other two expansions?
Yeah.
So wouldn't everything rip apart? Does that mean everything would rip apart?
Doesn't mean what?
Does this mean everything would rip apart? It goes exponential?
Well, no, it doesn't mean necessarily everything will rip apart. If you're holding hands with your mate and there's a weak tendency or a small exponential growth, it's not going to tear your partners away from you. Your grip may be stronger than the tendency for the expansion to pull him or her away from you. So no, it won't necessarily pull everything apart. But what won't get pulled apart is the clumpiness. On some average scale, on some long-distance scale, a scale which is large enough that the gravity holding things together is too weak to hold them together, yes, it will pull everything apart. It won't pull apart our galaxy. Our galaxy is concentrated and dense enough and sort of well above average energy density, so well above average energy density that it's being pulled together, in fact. It won't pull a solar system apart. It won't pull an atom apart. But it will pull apart a supercluster or a sufficiently big sample. And so it's a delicate question of what gets pulled apart and what doesn't. And we could try to be quantitative about that, and maybe I'll come back to it. But on the average, over very large scales, yes, things will all get pulled apart by this effect. Okay, so
Excuse me, a question. That last line, A equals e to the square root times. That implies no asymptotic limit, does it? Does that imply the vacuum line for?
This is it, asymptotically, it exponentially increases.
Right, but there's no upper limit. Keeps going.
If T is large, then that's big.
Yeah.
So I mean, doesn't A
T is large, it's very big.
So doesn't it mean that A even over little distances?
Say it again?
Doesn't it mean that A even over little distances pushes things very far apart? Is T
Time goes
very
on.
large?
Yeah.
Eventually, it would get.
But again, over small enough distances, it's counteracted by other forces. This can be modeled by a weak force pulling things apart. On the average, if things were far enough apart and dilute enough, everything would expand with it. But there may be places where the energy density is sort of concentrated in lumps. Those lumps may have enough internal gravity to hold them together. So instead of the lumps expanding, the lump might even contract, but distant lumps will fly apart. So there is a lumpiness to the universe. The universe is doing two things simultaneously. The lumpiness is contracting ever into more lumpiness, but meanwhile, on larger scales, everything is separating and becoming more dilute. Yeah. Okay, so dark matter is not radiation, is part of this. There are two components to the matter energy density. One of which is familiar matter. It's the stuff which shines in the sky. And the rest of it is dark matter. What do we say? Dark matter is about 10 times as much as ordinary matter. But it has the same equation of state. And so from the overall behavior, just from the overall behavior, without knowing more, all you can say is there's a certain amount of matter. Yeah.
Is there anything interesting in the negative sign in front of that square root?
There's no negative sign in front of the square root.
Could be. Well, I mean, when you take the square root.
Oh. Yeah, there are two possible solutions. There are always two possible solutions. There's the universe and the universe run backward. Universe run backward contracts. There's always, the equations are always such that they admit two solutions, the forward-going thing and the thing which you would watch if you ran the movie backward. They're always both solutions. And it comes from the fact there's a square here, so when you solve for a dot over a, you take a square root, it could be positive or negative. Physically, of course, they're the same, but they correspond to watching it going forward or watching it going backward. Does that answer your question?
Well, it's not a contracting universe then.
It's not a question of whether. No. Okay. The universe. Let's forget for the moment this vacuum energy. In any case, you always have two solutions. Now, what are the two solutions? You see an object far from the Earth, and it has a certain kinetic energy and a certain potential energy. How is it moving? Well, all you can tell from its kinetic energy is what its overall speed is. You can't tell whether it's moving away from the Earth or toward the Earth. If you know something, we see it's not a satellite, it's not going around, but you see a distant object moving radially. We know it's kinetic energy. Is it moving toward us or is it moving away from us? You can't tell unless you know an additional piece of information, namely whether it's moving away from you or toward you. Its kinetic energy doesn't tell you. This is basically an equation telling you about the kinetic energy of something receding. It could be positive or it could be negative. Things, given where it is, it doesn't help to say that the Earth attracts. That doesn't mean that the object far away is moving toward you. It simply means that it may decelerate. If it's going away, it may decelerate. But there's no way that you can know whether it's moving away from you or toward you. That's an additional piece of information. All right, the additional piece of information is, at least with a normal concept of things, the universe is expanding with ordinary time. What if it were contracting with ordinary time? Would we know the difference? Hard to tell. Hmm? No, I mean... well, if everything was running backwards, including us, obviously we couldn't tell. Right. We would just be part of a movie running backwards, and we would speak backwards, we would think backwards. Right. So turning, and it would just be a change of variables from t to minus t. Right. So there's always that ambiguity in the equations, and we always pick out, more or less by definition, the expanding solution. Okay. The expanding solution, what is it that determines the direction of time when we say the future versus the past? It's thermodynamics. So it's the second law of thermodynamics, but we won't get into that today. There certainly is ordinarily a difference between past and future, but let's not do that now. All right, let's summarize now the three components of matter in the universe. These are all called matter, even though this is just plain vacuum. They're all called, well, again, ambiguities of terminology. That's matter, that's radiation, that's vacuum. All right, but collectively, they're all called matter. Maybe we should just call it stuff. Stuff, let's call it stuff. All right. Matter, meaning this, has two components, dark matter and luminous matter, of which there is more dark matter. The radiation today is very, very weak because it's been redshifted, but at some time in the past, when the universe was about 1,000 times smaller, because of the difference in the way the radiation depends on scale factor, at some time in the past, the radiation was the dominant component. And in the future, a long time future, as the universe expands, both of these will get smaller and smaller, and this does not get smaller and smaller. So in the remote future, the expansion of the universe will be governed by the vacuum energy. All right, let's draw some graphs just to illustrate. I'm drawing these graphs because these are the kind of graphs you'll see if you read a Scientific American article. Unfortunately, astronomers and astrophysicists have this terrible habit of taking simple graphs and superimposing them upon each other until you have so many things on the graph that you can't possibly figure out what's going on. But you could take them apart and say, you know, I'm taking the graphs apart and one by one. All right. No, I'm not going to take them apart. I'm going to put them on top of each other. I'm going to be an astrophysicist today. All right. We could plot as a function of scale factor. This is a function of the expansion of the universe. We could plot energy density. And there are three kinds of energy densities. And let's put all three of them on the same graph. It does help to put them on the same graph. All right. We can start with the easiest one. The easiest one is rho naught. It's just constant. It does not depend on A at all. We're not talking about now A as a function of time. We're talking about rho as a function of A. It's just constant. It looks like that. It doesn't dilute. Diluting would mean going to zero. Now let's take radiation. I'm working upward. Radiation is very big when A is small and very small when A is big. All right? So it falls off quickly. Here's radiation. It falls off quickly. Now, finally, sort of in between is matter. Let's make matter in blue. Matter falls off like 1 over A cubed. That means at small a, it's smaller than the radiation component, but at large A, it's larger. And so it crosses over. It crosses over, but also goes to zero eventually. Let's imagine now, all right, so there's a crossover point here. At that point, that's the point at which the universe goes from being radiation-dominated to being matter-dominated. Right? That happened after about 10,000 years. Very, very early in the history of the universe. The universe was very, very hot, much too hot to be transparent, and so we can't directly look back to that point. It was about 100,000 years, in other words, another factor of 10 later when the universe became transparent. It's in here someplace, but this is the crossover from matter. Let's write down. This is radiation. This is matter. This is vacuum. And then later on, when the universe got bigger, there was a crossover between matter and vacuum. What's the total energy density? Well, very early it was dominated by radiation. So let's get a red pen here. Very early it was mostly just radiation. So it was this. Then when it crossed over, it was mostly matter. The radiation became less important and it tracked along here. Well, eventually it just moved on to this line. But then, if we waited long enough, both of these became smaller than the vacuum energy, and so it gradually shifted and just became vacuum energy. So there were three eras, if you like. The radiation-dominated era, everything was much too hot to be transparent. The matter-dominated era, where most interesting things of cosmology happened, but not life. Life formed someplace around here where the crossover happened. This crossover is about, I don't know if it's 4 billion years, 5, 6 billion years, some number of billions of years of order of magnitude, the age of the universe. So more or less, we're in the transition region, more on the vacuum side than on the matter side. We're in here somewheres, but we're in this transition region. Now, let's talk, how do we know this? What's the observations that tell us that this sequence is what happened? And for that, we look at another graph. The other graph is not energy density versus scale factor, but scale factor versus time. It's simply the time history of the universe and how it grew. So here it is. Early on, the dominant form of energy was radiation. The others were negligible. And the implication is that the universe grew like t to the 1/2. T to the 1/2 is a parabola turned on its side. So if there was only radiation, it would go like that. But then at some point, the crossover, matter became more important than radiation, but still, it's more important than anything, still more important than vacuum, and it became more important than radiation. And at that point, when I say point, of course, I mean a range of times, but over a range of times, let's put it in here somewheres, it made a transition. And instead of going like t to the 1/2, it went like t to the 2/3. It didn't have a bump like that in it, but that's... So it made a transition from t to the 1/2 to t to the 2/3. As I said, we can't see back that far. It happened too early, so let's put it early. T to the 1/2, then t to the 2/3, and then somewhere in here, something very dramatic happened. Instead of following something like this, the universe began to to expand in an accelerated way. Why is it called accelerated? It's called accelerated because exponential expansion, an exponential is accelerated. That's what does acceleration mean? It means the second derivative, second time derivative of something. The second time derivative of an exponential is as big as the exponential itself, so it's accelerated expansion, but just exponential expansion. Where are we? We're somewheres around over here, maybe a little bit further out. We've seen enough of this exponential to know that it's there. We've seen enough of the exponential to be pretty sure that it's behaving like an exponential. At the present time. But how do we see these different behaviors? All we have now, we're at a certain time. How do we see? We can't see the future, but we can see the past. And the way we see the past is by looking out with large telescopes out to distances that correspond to earlier times. So when we look far out and we count galaxies and we see how the galaxies are moving and how their motion correlates with their distance, effectively what we're measuring is the Hubble constant as a function of time, but equivalently we're measuring this whole curve. We can't see back directly to the radiation-dominated era. Most people believe it was there. But we can certainly see the matter-dominated era and the transition to the cosmological constant-dominated era. So
this is sort of looking at a certain distance and measuring the Hubble constant and for that distance at that time, and then a later time and an earlier time, and you get this curve when once you're done with it.
Yeah. So it's a reconstruction, but it's not a very difficult reconstruction. If you, what's difficult is the observations. But once you have the observations and you've cleared out all the garbage and the systematic errors and everything else, it's a relatively simple matter to reconstruct the time history of the scale factor. And it is completely consistent with this transition from matter-dominated to cosmological constant-dominated. As far as we know, this is really tending to a pure exponential. We don't know anything else that looks like that. And what that means is the universe is going to exponentially increase. Apart from those things which are attached to us by gravitational cords or other kinds of strong forces, things which are sufficiently far away that they're participating in this overall expansion, those things will eventually just disappear through the horizon. I haven't told you yet about the horizon, but now it's now easy to figure out what the horizon is. Yeah, let's see if we can understand now the idea of the horizon.
I have a quick question about that, because there seemed to be an indication what you said earlier, that the surface of last scattering kind of fades into the horizon instead of going through. I didn't quite understand.
Well, the surface of last scattering it's not moving. It's the place where the radiation, sorry. Yeah, it is moving. As time goes on, the surface of last scattering will move out, but it will never get past the horizon. In other words, we will see the radiation that we will see will be coming as our own time goes on. The radiation will be coming from a place which gradually moves out, which is equivalent to the radiation cooling. We will see a cooler and cooler universe, which is equivalent to the universe expanding.
How is that different from the local galaxies moving beyond the horizon?
No, it's not the same thing. At a later time, the radiation that we see will not come from the same atoms as the radiation that we see now. It will come from atoms which were further away at that time. So it's like seeing deeper and deeper and deeper into the universe rather than seeing something moving away from us.
To put a chronological time frame on this thinking on this, like 50 years ago was about the time when they determined the early portion of the universe, right? The Big Bang Theory started. Yes, it was kind of clarified then. And that predates my high school education. It dates me. I'm pretty close to it. It was the late 50s, early 60s. I graduated in 56. So. And then the vacuum energy portion of it, that's like 10 years ago, right? It was 1998. So all prior stuff was like the matter dominated and was pretty much the normal thing.
Matter dominated was believed to be the way the universe is, yeah. There's another difference also. The other difference is what we have left out so far. Where's the FRW equation? We're going to put it back next time. A dot over A squared is equal to rho. I'm leaving out 8 pi over 3, blah, 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 and G. Rho times stuff. And then there was that other thing, minus K over A squared. Remember that? We've left that out. Now, numerically, it seems to be very insignificant, and so leaving it out seems okay numerically. But it really is conceptually important. It determines whether the universe is closed and bounded or whether it's open or whatever it's doing. Now, in the old days, before there was a cosmological constant, and it was believed that the universe was closed and bounded, so that this term was there, then people would have drawn curves which look like this. They would have drawn curves where the universe expands for a while and then recontracts, and followed by a crunch. This is nothing but the phenomena of something going up and then coming back down. All right? K here tells you whether the total energy is positive or negative. K equals 0 is right at the escape velocity. So in the early days of Big Bang cosmology, it was assumed the universe was closed and bounded, which meant that K had a certain sign. And nobody knew about vacuum energy. Einstein had rejected his child as a bad mistake. And so it was thought that the universe was matter-dominated with a net total energy below 0, which means that, just like this thing will come back down, the universe would crash. This was called the Big Crunch, and this was the Big Bang. Now we don't believe in this part anymore. Not that we don't believe in it. Mathematically, there was nothing wrong with it. But empirically, this K seems to be 0, to a high approximation. And there's a component in the energy which is driving this accelerated expansion. So to the best of our knowledge, the universe is not going to crunch.
I missed the time when the transition to the exponential occurred.
It's somewhere in the vicinity of about 5 billion years. Ago. Both ago and from the beginning. Remember, the universe is about 10 billion years old. Oh, okay, I don't remember. It's a fuzzy beginning. It's a fuzzy beginning, but it's order of magnitude the age of the universe, half the age of the universe. Yeah. Somebody might look it up, and I don't have the number about it.
Two quick ones. One is that vacuum energy related to quantum vacuum energy?
Yes. Or at least we believe it is. Yes. All right, let me just tell you one more thing. Today, these energy densities scale differently with time. A1 of A cubed, 1 of A fourth. Right. But today you can ask, what is the relative abundance or the relative magnitude of the different components of energy? So I'll tell you what the relative abundance are. Now that you know what they mean, relative, not absolute. Or I could also tell you absolute, but relative abundance. The biggest single one is the vacuum energy, rho naught. Let's write rho naught over rho total, okay? This just means the fractional. Rho total means the sum of all the energy densities. This is today. Today is about 70%, 0.7. So most of the energy, that means that we are well into the region dominated by the vacuum, but not that well. I mean, it's not, you know, it's not 0.999 vacuum energy. It's 0.7. Okay, today. Rho matter is today about 0.3. Rho radiation is negligible, very, very small, about, I think, about 10,000 times smaller than the matter energy. So this is very, very small, essentially zero, not much there. But the rho matter comes in two pieces. Rho dark plus rho, let's call it luminous. The dark matter, well, let's see, the luminous is about 5%, 0.05. And this, I guess, is about 0.25. That's the composition today. That's the composition today. If you run it backward or forward, the ratio of dark matter and luminous matter will stay the same. That's because they both scale like 1 over a cubed. That'll stay the same. So the ratio between these two, but the, oh, I'm sorry, I should divide by rho total. Over rho total. But depending on the era, on the time, the relative abundance of these three will be different. If you go into the remote past, radiation dominated. If you go into the mid-past, the moderate past, matter dominated. Go into the remote future, this will become essentially one, and it'll all be vacuum energy, at which point the universe will just exponentially increase, cooling as it increases, and it's interesting to think about the astronomers of that period. They will live in a universe and look around them and see nothing, except for the immediate galaxies which will be infalling toward them. I think the Andromeda and the Magellanic Clouds are about the only thing that they'll see out there, and by that time they will have merged anyway. So they'll see a single galaxy. This will be about in 100 billion years. It'll take 100 or 150 billion years or something like that. Our galaxy will be completely isolated. Oh, another question is, where is the horizon? How far away is the horizon? So to figure out where the horizon is, what we want to do is figure out what the Hubble constant is. Let's figure out the Hubble constant. Here we have it. Well, let's just write down the equation. A dot over A is equal to, what is it, square root 8 pi g over 3 rho naught. That's it. That's the Hubble constant. Did I get everything? I think so. Yeah. And in the future. And in the future. In the remote future, there will only be rho naught. So this is not quite true today. The other energies are in there. But in the future, wait a little while, mostly it'll just be rho naught, and this will be the form of the equation. This is also the Hubble constant. And so if we write the equation that Hubble originally wrote, namely velocity is equal to distance times Hubble, square root of 8 pi g over 3 rho naught, then we can ask the question, how far away do you have to be so that the outward recessional velocity is the speed of light? And all you have to do is substitute speed of light in there. 1. In our units, 1. And that tells you that the distance to the horizon, The distance to where things are moving away from you with the speed of light is 1 over square root of 8 pi g over 3 rho naught. It's this distance which is about 10, 12 billion light years away. But notice that it doesn't change with time. Once this exponential expansion sets in, the Hubble constant stays constant, and the distance to the horizon is just fixed. What is the horizon? The horizon is where things are moving away from us with the speed of light. So as the galaxies in the universe expands, one by one, the galaxies will pass through this horizon, and we can just wave goodbye to them. They will get, actually what will happen to them is they'll get more and more and more redshifted until we just can't see them anymore. That will happen to just about everything with the exception of the nearby Magellanic Clouds and Andromeda Galaxy. And so the astronomers of that period, unless they have good history books to remind them of what people knew in the past, will be very puzzled. They will think that the universe is an island in an otherwise infinite sea of empty space. They will not be able to see the black body microwave background radiation. It will be too thinned out, too redshifted. They will have no way of even knowing there's a cosmological constant because they won't see anything receding away from them. There will be nothing out there. So we can imagine them being very puzzled and thinking that the universe was one galaxy and nothing else.
Read the early books. Read the early books.
If the early books are still intact.
Get out of the
Yeah, that's actually very hard to keep information over long periods of time. I mean, if you just look at our brief history.
Back to literacy.
Well,
but certainly you can even go back into time, and you can say someone back there that there may have been other terms, and they said, well, now it's only year 3, and they say, well, in year 5 billion, they're going to only see this, this, and this.
Right. It would be extremely hard for the astronomers at year 3 to know that there was a cosmological constant because it was so subdominant. But it's also true that there were no astronomers at year 3 because it was too hot. It's a curious fact that that all the cosmological parameters point to about the same scale of time as the evolutionary time scale for evolving a human being. A couple of billion years to go from the, well, first of all, you've got to get the sun to cool. I mean, you got to get the sun to form and so forth. That takes a billion years or so. But then the time scale for evolution is what, 3 billion years or something? 4 billion years? Yeah, you got to get the metals. So the time scale for evolution of a complex organism was about 4 billion years. The first 3 billion of which was simple single-cell things.
Yeah, and it required stability of things for that long for evolution to take place. But you did say that the surface of last scattering would not go over the horizon. It would just get weaker and weaker. So the galaxies, other than our local cluster, are going to move through the surface of last scattering.
Yeah, except that we won't be able to see them as galaxies at that point. We'll just see them merge into the, they'll get so redshifted that they'll get redshifted down to the same 3 degrees, and it'll be hard to distinguish them from any of the other black holes.
So the surface of last scattering depends on where you are, because the astronomers in those galaxies are not going to see themselves moving through the surface of last scattering.
Oh, they're not going to see, no, they're going to see us moving through the surface of last scattering. Right. Everybody's on an equal footing.
I seem maybe erroneously to recall that in the first lecture you said there's reason to believe that the universe, the size of the universe is
Reason to believe what?
The size of the universe is some orders of magnitude larger than what we can see now.
Yeah.
Is that evident from what you said?
Not yet. Not yet. It becomes evident when we talk about measurements of the geometry of space. And we can measure the geometry of space, basically measure the sums of angles of triangles. But how big a triangle? Very, very big triangles. What we can do, here we are at the center. We look out and we see the surface of last scattering way out here. And we see some blob in the surface of last scattering. What is it? It's a blob of over-density or under-density or whatever it happens to be. Some kind of, the surface of last scattering is somewhat blobby. It's got some lumpiness in it. We see a lump, and we have very good reason to believe that that lump has a certain size. Okay? We draw a triangle. We also know with fairly good precision by now the distance to the surface of last scattering. So we draw a triangle, an isosceles triangle with two D's, and let's call it the third leg, call it L for length or L for lump. Okay? Now, if we have a triangle like this, and we know D's and L, we know this angle, theta. We know the angle if space is flat. If space is positively curved, then this angle would be bigger than we would estimate from Euclidean geometry. If space is negatively curved, this is going to be the subject of next week, negative and positive curvature. But depending on the curvature of space, we would either see this angle bigger or less, bigger or smaller or equal to what we would expect for Euclidean geometry. What do we find? We find that to about 2% or better, or 1% or better, that Euclidean geometry is correct. That means that space is flat. It is very much like measuring triangles from me standing at the center, looking out some distance, 1,000 feet or 100 feet or whatever it is, some object of known size out there, and looking at the angle and discovering that the angle is consistent with Euclidean geometry. I know the size. I see some battleship out on the horizon. Not quite on the horizon, in closer. I know that battleship is, how big is a battleship? How many feet? How many? 800 feet. I know that that's the battleship Missouri. Was Missouri a battleship? Yeah. The Bismarck. I see the Bismarck out there. Right. I see the Bismarck. The Bismarck is bigger than 800 feet, I bet. And I know just how big it is. I also have reason to think I know exactly how far it is. And I measure the angle, and I see that it satisfies Euclidean geometry with a flat Earth. Well, not quite flat. I don't know that it's exactly flat, but I know it's flat to a good approximation. That tells me that the Earth is bigger, significantly bigger than the distance to the Bismarck. Yeah, go ahead.
Yeah, this is good for battleships, but what's an example of an object out there that we know the size of?
We'll come to that.
Oh, next week?
Lumps, the largest lumps in the microwave background. And we think we know their size because we know how long it took them to evolve, and we know the speed of sound, and so a variety of things. But it's the largest lumps that are seen on the microwave background.
Would it also turn out that rho naught is not necessarily a constant, just like the Hubble constant is not a constant?
Experimentally, it's very close to a constant. Incidentally, when you read about it, if you read about it and you read about the measurement of W, if people tell you that they've measured W to be -1 to good accuracy, that's the same thing as saying that the vacuum energy is constant. So if you read in the Scientific American that astronomers have concluded that this strange parameter that they call W is -1, and it's getting more and more and more closer to -1, that's an indication that the vacuum energy is constant. And how close is it? It's something like 1 plus or minus, well, it can only go on one side, but to within about 10 or 5%, it's 1. -1.
Would general relativity work with a vacuum energy for which the equation state would not?
There are ways of making it not be constant.
So at least in principle, general relativity doesn't exclude the possibility of more radical vacuum energy.
But the vacuum energy is something which is good reason to believe is there. The other things, there's much less reason to believe is there. We'll come to it.
There's no singularity or anything at W equals 0, is there? Things are well defined.
No, there's nothing. W equals 0 is just non-relativistic cold matter. W equals 0. W equals 1, not -1. It's believed, there's good reasons to believe that W has to lie between -1 and 1. W being -2 would really violate general relativity. W equaling +2 will also violate general relativity.
Would violate special relativity. So the density calculation for matter and for radiation, you assume that the energy was constant, and then you adjusted the scale factor to figure out the formula.
No, I did not assume it was constant. We used that the change in energy is PdV.
Yeah.
Minus PdV. So we assumed that if we had an imaginary box that was following a unit volume and the universe expanded, that the imaginary box moving along with it, that work would be done on the walls by the expansion, and that would account exactly for the change in energy. Okay. Now this can be done using there are fancier ways to do this.
But that doesn't assume the total energy was fixed, right? And so the larger volume means a lower energy density.
Okay, yeah, that's right. The total energy is fixed.
So that's true for the first two, but for the vacuum energy, the density is constant. So that implies the energy.
As long as this equation is satisfied, that's energy. That is energy conservation. All right. Well, remind me to talk about energy conservation. The trouble with energy conservation is that the energy of the universe is 0, so it doesn't say very much.